All right, good morning. Hope everything's going well. Shoot, that's kind of loud, sorry. Well, hopefully you saw the lecture that was posted for Friday and have had a chance to look at that. We're going to pick up with the end of stereochemistry today and then move on to chapter 6. Probably today will be all that we will spend on chapter 6 and then move straight into new reactions in chapter 7 and 8. Okay, so last time I mentioned that enantiomers have the same chemical and physical properties, except the place where enantiomers can be different, two places. First, how they interact with polarized light, and also how they interact with other chiral molecules. So this issue of how they interact with plane polarized light, that's in, I think, sections 12 and 13 maybe of the Smith text in chapter 5. Optical rotation, that's pretty straightforward to understand, so I'm not going to really spend any time on that in class. You should do some practice problems in which you use optical rotation information to calculate how much more of one enantiomer you have than another in a mixture. Again, it's pretty simple, so I don't think it's worth a lot of time in class. I'd rather spend time on the hard stuff in class, but be sure you look at that. There's some, I believe there's at least one practice problem on the practice exam about that. It's pretty easy to write a test question about enantiomeric excess and optical rotation. And in any case, if you've got standardized exams in your future, MCAT or DAT, it's possible that that kind of thing will be on there, so you want to be prepared to answer that. I'm not going to spend any time on that today. What I do want to talk about is this issue of how enantiomers differ in how they interact with other chiral molecules. Really, this exception here, how they interact with other chiral molecules, is actually related to this principle that diastereomers do not have the same chemical and physical properties. And that's true for molecules that are actually diastereomers of each other. That's also true for non-covalent complexes of molecules that are diastereomers of each other. So I think I showed you this close-up image of a crystal structure. Crystallography, X-ray crystallography is how we visualize atoms in large and small molecules, actually. You crystallize them, shoot X-rays through the crystal. The diffraction pattern tells you something about the way the atoms are oriented. And this is the overlay of two crystal structures of the same protein. One of them has the S enantiomer of this molecule, and the other has the R enantiomer of this molecule. The protein itself isn't that important. I think I explained last time it's involved in phenazine biosynthesis. Phenazines are dye molecules that are also redox active, and so some bacteria synthesize them for various purposes, antioxidant purposes, also they can be virulence factors. Anyway, that story doesn't matter other than that you have the same protein in gray. You can tell that there's two proteins overlaid because everything doesn't entirely match up. In one of the complexes, you've got the S enantiomer. In the other complex, you've got the R enantiomer. Now, what you have to know about proteins is they are chiral, and they're all made of amino acids that have the same kind of chirality. So these two protein complexes, you have the same protein but two different enantiomers. That means these two protein complexes are actually diastereomers of each other, right? Because the protein, all the stereocenters in the protein are the same. The only thing that's different is the stereocenter in the ligand that's bound to the protein. And you can see these two complexes are different in the sense that when the S enantiomer is bound to this protein, you can see the carboxylic acid on the protein is interacting with this amino acid side chain here. This happens to be a side chain that's positively charged, so thinking about intermolecular forces, it makes sense that a negatively charged group on a ligand, small molecule, should be interacting with a positively charged group on the protein. Similarly, but for the other enantiomer, that carboxylic acid group is not interacting with the same side chain. It's interacting with a different one. Small, that may be a small detail, but actually that can have dramatic consequences. Yes?
How is it a diastereomer and not an enantiomer?
The two molecules are enantiomers of each other. The complex of those two molecules with the same protein are diastereomers of each other, because the protein has stereocenters too. And remember, enantiomers have to have opposite configuration at each and every stereocenter. Diastereomers have opposite configuration at least one, but not all. And got it? Okay, good. All right, so enantiomers will fit into the active site of a protein differently, and that will have different consequences. In this case, it's just a difference in binding constant. One enantiomer binds more tightly than the other. In other cases in biology, one enantiomer may be highly active as a drug and the other may be completely inactive. Or one may be highly active as a drug and the other might be toxic. And there's some cautionary tales described in your test if you've ever heard about thalidomide as an antiemetic in pregnancy to prevent morning sickness. One of the enantiomers was active, the other enantiomer was a teratogen, which is exactly not what you want to be taking at the time baby's developing, right? And it was even more difficult than that because some drugs will be metabolized in a way that converts one enantiomer into a mixture of the two, and so you can't actually avoid having the wrong enantiomer. So these are things that drug companies worry about all the time. And so now I want to tell you a brief story about enantiomers and drugs and patent evergreening. So patent evergreening, if you want to understand a little bit about drug development, from the time that you file a patent on a drug, you have something between 17 and 20 years of exclusive rights to market and sell that drug. Now, often the patent is filed long before you actually complete the clinical trials and long before you can market the drug. It's a strategy, and you have to make sure that the other companies are not figuring out what you're doing. In any case, the clock starts ticking, and research and development is really, really expensive, and so for the survival of drug companies, we feel really, really bad for them, I'm sure. They have to be able to have a window where they can make money off the molecules to fund all of their research. So when a drug goes off patent, what that means is other companies now can synthesize the drug. They have to prove that it's exactly the same thing, but if they can do that, then they can start marketing the drug too. That's called when the drug goes generic, all right? So there are many drugs today which used to be on patent, but which are now generic. For example, the drug Zoloft prescribed for depression that's the brand name. The actual name of the molecule is sertraline hydrochloride. That's now available generic, and the price goes down, which is great for us, but not so great for the drug companies. So there are strategies for extending the lifetime of your patent. And that doesn't involve, going to the FDA and saying, please, sir, could we please have exclusive rights to market our drug? It's a little bit more insidious than that. So, behold, the drug citalopram. This was marketed under the brand name Celexa in the 90s and early 2000s. It's indicated for depression, and it was discovered in 1972 by a company in Denmark. And it was originally developed and marketed not as, it's got a stereocenter, but it was marketed not as the pure active enantiomer, but as a racemic mixture of two enantiomers. Some of this gets into the weeds a little bit. We're going to see when we start doing a lot of reactions that it's very difficult to take a molecule that is not chiral and introduce a stereocenter into it in such a way that you only get one enantiomer. That may not make a whole lot of sense right now, but you'll see that a little bit later. It's pretty straightforward to take a molecule that is already chiral and already has a stereocenter and convert it into another molecule which is also chiral. Chirality begets chirality. It's hard to get chirality from nothing. So here I show you both the R and the S enantiomers of this drug, citalopram. Now, the FDA's known a long time about the issue of the other enantiomer having a problem. And so you have to demonstrate through safety and efficacy trials, if you're going to sell a mixture that's a one-to-one mixture of both enantiomers, you have to demonstrate that it's completely safe, all right? So this molecule was sold as a one-to-one mixture of enantiomers. That is called a racemate. Sometimes a one-to-one mixture of enantiomers is called a racemic mixture or a racemate, one-to-one mixture of enantiomers. And again, only one of these was active. It was the S enantiomer. But as long as the other one doesn't cause problems biologically, it's just cheaper to do it this way, right? Separating out two enantiomers is difficult because they have the same chemical and physical properties. So there are plenty of tricks, and that's beyond the scope of our discussion. But just understand that that this drug was originally marketed as a one-to-one mixture of enantiomers. Oh, I should say, some of you have heard this term. Citalopram is a selective serotonin reuptake inhibitor. It helps serotonin last longer as a neurotransmitter. It's in the same class of molecules as Zoloft, like I mentioned. This was, as I said, developed in the 70s in Denmark. It was approved for use in 1989, and then FDA approved it in 1998, and the patent expired in 2003, okay? So at that point, the Danish company that marketed the drug had a problem, which is now anybody can make it and sell it. So your exclusive profits go down dramatically. So one of the classic strategies is that you develop an enantioselective synthesis, and we're not going to worry about how that happens, but where you synthesize only the active enantiomer. It's a whole area of chemistry for how to do synthesis enantioselectively. But they either separated or synthesized only the enantiomer that was active, and they called it S-citalopram. Cute, huh? Same company. They marketed it with a different name, so they initiated the development of this drug in 1997. So they were preparing, right? They knew they had 6 more years of patent exclusivity, and they were like, we got to do something about this. So they began development of the S enantiomer. Their new drug application was filed in 2001, FDA approval in 2002 with patent expiration in 2012. Okay. So, and this was actually challenged in court because some folks were like, hey, wait a minute, I mean, you already disclosed that molecule. But courts ruled in 2006 that the patent was valid on this S enantiomer, that you could patent a process in addition to just the drug. And so they were able to maintain exclusive rights to the S enantiomer through 2012. So almost 10 more years on a patent. Go ahead.
Do you know who the plaintiffs were in that
Do I know who the plaintiffs were? No, but Wikipedia does. There is an article about it. Yeah. Plaintiff, yeah, I know that word. I watched an episode of Suits the other day, so I know that word. Okay. So during all this time, other companies from 2003 on could make the racemic mixture of enantiomers and sell it, and they did. But the company had to claim, and did claim, that it was better to take just the pure enantiomer. Okay? Now there's a cost-benefit analysis here. So in the article I read was all this money's in British pounds in like 2009, so who knows what any of that means. But 28 tablets of 20 milligrams each was 1.26 British pounds sterling in 2009. Whereas the same 28 tablets of 10 milligrams of S-citalopram was 14.91 British pounds sterling. By the way, are we comparing apples to apples here? What's with the 20 milligrams versus 10? Why is that a fair comparison? Because the racemate only has 10 milligrams, 20 milligrams of the racemate only has 10 milligrams of the active compound. Okay, more than 10 times as expensive. You can see the people at the corporate offices tweedling their mustaches and laughing. Now there were, so the question is, bang for your buck, is it better to prescribe, if you're a physician, is it better to prescribe the pure enantiomer at 10 times the cost or the racemate at a fraction of the cost? And the question really has to do with, does this other enantiomer really cause problems? And there are various reviews and meta-analyses in the case of citalopram suggesting that there's maybe a modest benefit to S-citalopram in terms of effectiveness and tolerability. All drugs have side effects. It's perhaps, you could argue that the side effects should be lower if you're not throwing in 50% of this other molecule that does nothing active but may still have other side effects. So a review and meta-analysis suggested that there was maybe a modest benefit to the pure enantiomer, but maybe not enough to justify more than 10 times increased cost. Okay, so at some point in your future, you may be sitting in your office and a sales rep from a drug company wants to come talk to you, and please don't let them push you brainlessly into prescribing the expensive designer enantio pure version of a drug if the generic one was already doing pretty well and pretty well approved. Another classic example of this that you will see, you want to read more about, is the case of Nexium and Prilosec, or their generic names are omeprazole and S-omeprazole. Okay. All right. So with that, I want to maybe let's do a few sort of chiral, not chiral, are they enantiomers or diastereomers from the practice exam. Just want to give you a chance to figure out how to get started on some of these problems. So, but I guess before we do that, any questions or, I don't know? Good, because I already told you everything I know about that stuff. All right, so chiral or not chiral? In a multiple choice exam, I try to avoid the problem. I realized that if I did A chiral and B achiral, that was going to cause people trouble because there's an A in both of them. So we'll say not chiral. So here's one from your practice exam. I think you're going to hate this one. Some of you are looking at that thinking, what do I even do with that? So first, build a model. Or try to identify a ring and simplify it and draw it from the side rather, or from above rather from the side. So I notice that there is a 5-membered ring here. 1, 2, 3, 4, 5. And I notice that on carbons 5 and 3, carbons 5 and 3 are both attached to the same carbon. There's like a bridge between the two of them. So from our perspective, what would that look like? Well, you'd almost have a wedge here and a wedge there. Same carbon. All right. And then on top of that is a BR group, and that's going to be kind of hard to draw unless I do it this way. So you'll have to understand that there's a bond here sort of coming out towards you, hovering over the ring, and another bond here sort of again coming out towards you and hovering over the ring. All right, that one you may want to build a model of. So chiral or not chiral? What do you think? Well, one way to begin might be to look for stereocenters. We could highlight stereocenters, which are carbons that are attached to 4 different things. So I do see a couple of stereocenters. There's one here and one there. The classic way to test whether something is chiral or not is to simply draw its mirror image. Maybe I'll rotate this. That's fine. Let's just draw the mirror image. What's not on? Sorry, can you say that again? I didn't quite hear you.
You drew the wedge on carbon 2.
Oh, yeah, all right. I didn't like how I drew it anyway. All right, so that's our overhead view. We'll draw the mirror image. Chiral or not? What I said before still applies. 5 and 3 are still stereocenters, but gasp. They're the same. And the reason they're the same, even though they have stereocenters, is because you've got a plane of symmetry in this molecule that sort of contains atoms 4, this one, which up top, which I guess we can call atom 6. The plane of symmetry contains 4, 6, and bisects the bond between 1 and 2. In other words, that mirror plane of symmetry is right there, which makes the molecule not chiral. It is a meso compound. All right. If that one's difficult for you to see, there's not much I can do to help aside from building a model. If you want to come to my office and make me build the model for you, I can do that. Probably worth your time to sit down and build the model and convince yourself. Okay? All right. Let's do another one. Chiral or not chiral? Okay, if you're confused, remember the definition of chiral is a molecule that is not the same as its mirror image. So your fallback is draw the mirror image and see if it's the same thing. Well, come on, do it. I'm waiting. Okay, so what's your conclusion? Not. That is correct. It is not chiral because the molecule is exactly the same as its mirror image. All right. Are there any stereocenters in the molecule? Oh, sorry. Go ahead. How do I know which way to orient the molecule? If it were on its side, would it be any different? No. If it were on its side, it's still not chiral. So, though it's true, you're right, I cheated a little bit because I drew it in a way where all I'd have to do is slide things over to convince you that it was not chiral. But had I drawn it this way, and then drawn the mirror image, all I would need to do is a little bit of steering wheel action, and that would still show you that it was right. Is that your question or no? Yeah? Okay. Okay. Are there any stereocenters in that molecule? No, there are not. Why? Is that carbon attached to the same thing? Now, you can't just stop there. It has to be the same all the way around, right? If these were two carbons and then there was something different over here, then all of a sudden, yeah, it would be a stereocenter. But because they're the same all the way out until they join, then yeah, those are not stereocenters. Okay, so definitely not chiral. What is the relationship between the molecule we just drew, which is not chiral, oops, and this molecule? What is the relationship between these two? I'm hearing the word cis and trans, and that's true. You've got trans and cis. I'm looking for a particular word about whether or not, what kind of stereoisomer they are. Diastereomers, because if they're not enantiomers, they have to be diastereomers. So you can see that two molecules that are diastereomers both might not be chiral. The concept of diastereomer is not related to the concept of chirality. A diastereomer, two diastereomers may or may not be chiral, but they're not enantiomers. Okay, let's see. Yes?
The first two ones I drew, like the mirror image of?
No, here?
Like on this compound. Yeah, they're not meso.
Right, these are not meso compounds because
They don't have a
there's no stereocenters, exactly. A meso compound is a word we reserve for molecules that are not chiral but nevertheless have stereocenters. Okay, yes?
The one on the left, isn't like exactly the same on both sides too?
Yes, that's why it's not chiral. We drew the mirror image, We drew the mirror image and convinced ourselves that because it's identical to the mirror image, it is not chiral.
So why is that one a meso and the other one?
They're both, well, because there's only one molecule there. We call this a meso compound because it has stereocenters. But is not chiral on account of it's the same as its mirror image. Okay? So two different concepts here. Both of these molecules are not chiral. They are the same as their mirror images. The molecule on the left has stereocenters, and therefore it is a meso compound because it is not chiral but has stereocenters. The one on the right, just not chiral. Yeah. Yes?
What are the four things on the left that makes it a stereocenter?
Four things on the left that makes it a stereocenter. Let me move the number 5 there. Hydrogen, carbon, carbon, and carbon, where these two carbons, 1 and 4, are different from each other because they're attached to different things. Same thing with 3. 3 is attached to, and maybe it's easier to see from the side perspective. 3 is attached to carbon 2 and carbon 4. Carbon 2 and 4 are distinct because they are attached to different things. And then this hydrogen, and then carbon 6. Okay. All right, so that's going to take some practice. Probably you want to spend some time with your model set, convincing yourself that of what we've talked about. All right, that is stereochemistry. And again, please make sure you know how to do the optical rotation stuff. It's not hard. You'll be able to figure it out. So, chapter 6 is sort of our last introductory chapter in this class. And chapter 6 is about thermodynamics. Marone, you hate that word. And here's one you hate maybe even a little bit more, kinetics. Thermodynamics is why reactions happen, and kinetics is how. Okay? So let's deal with thermodynamics first. The why behind reactions happening is all contained in what I'm about to write here. And you swore in your wrath that you would never, ever look at that equation again, and yet here it is. Whether a reaction can happen depends on whether the free energy for that reaction, the free energy change associated with that reaction, is favorable or not. That free energy change is related to equilibrium constant through this equation. And if you know what the gas constant is, and you know what the temperature is, and you know what the equilibrium constant is, then you can say what the delta G is. This is a little bit of an aside. I'm going to write it down just so you're aware of it, and I may talk about it as we discuss various reactions. 1.3 kcal per mole, 1.36 kilocalorie per mole difference in free energy at 298 Kelvin is associated with a factor of 10 in equilibrium constant. So that's nothing to memorize, but it's something that I will use occasionally to give a sense for how big of a free energy, what big a difference a free energy change makes. Now let's talk about these numbers over here. Delta H is enthalpy. And this one actually is probably the most difficult to really understand what's going on. Entropy is a little bit easier in the sense that I think we all have an idea of what disorder means. my two oldest sons are both students here. They live in apartments with 5 other guys. They really understand what disorder means. And in fact, they're probably major contributors to this. Okay, so let's talk first about how to think about enthalpy. The issue in enthalpy is related to, for reactions, the strength of the bonds that you form versus the strength of the bonds that you break. And if we were to broaden this out a little bit, we could substitute bonds. We could add into our description of enthalpy not only the strength of the bonds formed, but also the strength of the non-covalent interactions you form in a process versus the non-covalent interactions that you lose. But bonds right now will do nicely since we're going to be focusing on reactions where bonds are changing. So the key issue with enthalpy is, are the bonds you form more or less stable? Are the bonds you form stronger or weaker than the bonds that you break? The entropy issue is an issue of more or less disorder. And there are a couple of ways that you can have more disorder or less disorder in a reaction. For example, if you take 2 molecules and you bring them together to get just one, you might expect disorder to decrease, right? Because you take 2 things that can move freely and now they're just one thing that can move freely but less freely than the 2 things, right? Alternatively, if you have a reaction where one thing splits up to become 2, then you might expect entropy to increase. And then finally, there are some reactions in organic chemistry in which you have a long linear molecule with a head and a tail, and you cyclize to form a bond between the head and the tail groups. And suddenly, the bonds that were free to rotate in this linear chain are constrained by the ring. You've seen, for example, that there are tons of different conformations that an acyclic molecule might be able to have, but for a 6-membered ring, there are only 2. There's the chair and there's the other chair, right? So cyclizing molecules can often result in entropy that's can result in a decrease in entropy or a decrease in disorder. All right, let's talk about this issue of bond strength. So we can have an idea of the strength of bonds formed versus the strength of bonds broken. We dealt at the beginning of the class with hydrogen bonding. We talked about a 1s orbital on one hydrogen and a 1s orbital on the other hydrogen, forming a sigma bonding orbital between 2 hydrogens and a sigma star antibonding orbital between 2 hydrogens. We said that this bond was such that 2 electrons got to move lower in energy. This distance in energy here is what we're going to call the bond dissociation enthalpy. In other words, how much energy do you have to put in to break this bond by exciting both electrons back up to the level that they were to begin with? So that's one way to think about stability of bonds. Another way to think about stability of bonds is to have, energy on this axis. And for a molecule where we have hydrogen A and hydrogen B bonded to each other, whoops, I don't know what's going on there. Let's have this be the distance R between hydrogen A and B. There is some minimum energy where there is some minimum distance where you have maximum bond stability. And if you push the 2 hydrogens closer, their nuclei start to repel, so energy goes up. But if you move the two nuclei apart, eventually you come up back to the level of the isolated hydrogen atom. The picture here on the right is basically the same thing here as on the left. This energy difference between the atomic orbital and the sigma bonding orbital is identical to this energy difference here. This is also the bond dissociation enthalpy. Or how much energy do you have to add to a molecule in order to break the bond? Okay? A way of describing this in sort of a picture is to show an actual reaction where you start out with hydrogen and you break the bond between the two hydrogens and get two individual hydrogen atoms infinitely separated. The change in enthalpy for that reaction is uphill by 105 kilocalories per mole. And that's also we're putting a number on it now, but that's what we call the bond dissociation enthalpy. Bond dissociation enthalpies are all related to reactions where you break a bond and one electron goes with one partner and the other electron goes with the other partner. I'm using a one electron arrow to show that. This is an arrow that's like our curved arrows we've used before when showing HOMO attacking LUMO, only there's one little flag at the top of the arrow instead of two. And that's a convention that you may not be used to, but the one flagged arrow is how you show motion of one electron. Another term you will hear with describing these reactions is that this reaction is homolytic bond breaking. Homo means each one gets the same. Lytic is a word that means breaking. You'll hear this in biology when they talk about lysis of something. Homolytic bond breaking is breaking of a bond such that both partners get an electron. So a lot of these reactions where you break a bond and get two atoms, each with an electron, a lot of these enthalpies are known, and if you know enough of them, you can start to make predictions about whether a reaction will be favorable or not. So let me show you how to do this with a reaction that looks simple on the surface. And I will say that enthalpy and free energy are what we call state functions. You learned about that in general chemistry. What that means is as long as you know the starting state and the ending state, you're going to get the same answer, irregardless, that is not a word, the same answer no matter how the reaction happens. So what this means is I'm going to draw a reaction and then I'm going to come up with an imaginary pathway for how that reaction might happen using a table of homolytic bond cleaving information. And even though the reaction doesn't actually happen that way, I'm going to get exactly the same answer for the enthalpy of the reaction as I would if I knew how the reaction actually happened. Okay? So what you do is first you look at this reaction and you ask, which bonds did I form versus the bonds that I broke? Okay, so over here, bonds that are present in the product that are not present in the starting material. Well, I've got a carbon-oxygen bond that wasn't originally there, and I have a hydrogen-chlorine bond that wasn't originally there, okay? And then over here, what about bonds broken? Well, I've got a carbon-chlorine bond that wasn't originally there, and then a hydrogen-oxygen bond that wasn't originally there. All right, so let's start with the bonds broken. I can go look up in a table for an analogous carbon-chlorine bond, what it would take to break that bond such that each partner has one of the electrons in that bond. And it turns out that the delta H for this reaction, the bond and dissociation enthalpy, is 331 kilojoules per mole. I hate kilojoules, but I didn't have time to convert the numbers to kilocalories, so that's what we're going to have to stick with. How about the hydrogen-oxygen bond? Again, I can look up in an appendix, a table in your text or at the end of the text that would show me that a reaction where each partner gets one of the two electrons in the bond has a bond dissociation enthalpy of 498 kilojoules per mole. I will point out that you can check yourself whether you're doing this right or not by remembering that breaking bonds always requires energy. Always. It's always uphill in energy. And that should make intuitive sense based on what we've talked about up here. It's always uphill to go back to where you were before you had bonds. That is something that may not ring true to you at the moment, because sometimes the way we teach people in elementary school and high school about reactions is we say, and breaking bonds results in a lot of releasing of energy. People will tell you that about ATP, right? ATP has unstable bonds, we break them, and that releases energy. False. What actually goes on with ATP hydrolysis is that you're replacing less stable bonds with more stable bonds, and that's what releases energy. You were only getting part of the picture there. Maybe that wasn't a thing for you. Maybe you don't even know what I'm talking about. We'll just continue onward. All right, so bonds broken. Now let's look at bonds formed. I form an oxygen-carbon bond. I can look up in a table the bond dissociation enthalpy for an oxygen-carbon bond. However, I'm forming this bond versus breaking it, right? So I could look up in the table that breaking a carbon-oxygen bond is worth plus 401 kilojoules per mole. But since I want to know about making the bond, I just need to reverse things, right? If it's plus 4.04 or if it's plus 401 kilojoules per mole to break the bond, then it should be worth minus 407 kilojoules per mole to make the bond, right? Does that make sense? So what I did there is, instead of worrying, oh, I can't find in my table of bond dissociation enthalpies, I can't find how to make this bond. No, I just find that bond, I see what the bond dissociation enthalpy is for breaking it, and then I just take the negative of that, and that's how much energy would be released if I make that bond. Then we can do something similar for the HCl bond. I'm going to just go straight to the backwards version where we're making it. And that would be minus 431 kilojoules per mole. So having done this, I can then add everything up together and see whether the reaction is favorable or unfavorable. So over here, for bonds broken, I have plus 829 kilojoules per mole. And over here, for bonds formed, I have minus 832 kilojoules per mole, which tells me overall that the enthalpy for this reaction should be close to minus 3 kilojoules per mole. Favorable, but not by a huge amount. Okay? All right. So that kind of thing is, the skills there are not that hard. You should practice that just to sort of see if you can do that. But if you can look stuff up in a table, and if you can add or subtract, then you're probably good to go. Next time we're going to talk a little bit about mechanism and then jump right into chapter 7. So I'll see you Wednesday.